Firstly, let's see the working principle of a reaction engine. An engine, like the one we find in airplanes, works based on Newton's third law, which states that for every action there is an equal and opposite effect. The driving force is a large mass of air or gases moving backwards, and the consequence is that this force pushes the aircraft forward, creating thrust. Types of reaction engines. Reaction engines are devices that generate thrust by ejecting mass, and they can be broadly categorized as either air-breathing or rocket-like. Air-breathing engines, like turbojets and ramjets, use atmospheric air as part of the propulsion process, while rocket-like engines, like solid and liquid rocket engines, carry their own propellant. Let's see the air-breathing engines and variations. Turbojet, a basic jet engine that compresses air, mixes it with fuel, and then burns it to create high-speed exhaust gases that produce thrust. Turbofan, similar to a turbojet, but with a large fan at the front that directs more air through the engine, increasing efficiency and thrust. Ramjet, a simple jet engine that relies on the speed of the vehicle to compress incoming air. It's typically used at high speeds where ram compression is sufficient. Scramjet, a type of ramjet that operates at supersonic speeds, allowing combustion to occur even at high velocities. Air-breathing engines are commonly used in aircraft, while rocket engines are used for space travel and other applications requiring high thrust. Explanation about turbofan. Turbofan engine works in 4 stages. The ingestion is the stage of the fan rotor. The blade wheel at the front draws in air, while in turbojet engines, all the ingested air flows consecutively through compressors, the combustor, and turbines. Turbofans separate the accelerated airstream behind the fan rotor. Here, too, a certain amount of air passes through compressor blades into the combustor, but the rest, known as the sheet flow, is not combusted. Instead, it bypasses the interior assemblies and is expanded in a separate nozzle to generate the majority of thrust, up to 80%. This cold bypass flow surrounds the hot exhaust gases from engine core like a sheet, ensuring a reduction in noise emissions. In compression, the portion of ingested air that flows into the engine core is compressed in the low and high-pressure compressors. Also known as a booster, the low-pressure compressor is responsible for pre-compression. The high-pressure compressor handles main compression and offers a high degree of efficiency and low weight thanks to its innovative bliss principle, where the blades and disc are manufactured as a single part. After compression, the air flows into the combustor. This is where fuel injection nozzles create a mix of fuel and air, which is then combusted at a temperature of approximately 1,700 degrees Celsius. The buildup of heat causes the gas to expand to several times its original volume and escape from the combustor at high energy. The hot gas races to the high and low pressure turbines, each of which has several turbine wheels and numerous blades that are rotated by the exhaust gas stream. This causes the stream to expend up to 60% of its energy to drive the booster, compressor, and fan. This happens by way of 2 concentric shafts. The outer shaft, which couples a high-pressure turbine to the high-pressure compressor, and the inner shaft, which connects the low-pressure turbine to the booster and fan. Only then do the combustion gases leave the thrust nozzle, generating an additional burst of residual thrust. Efficiency. Propeller engines are most efficient for low speeds, turbojet engines for high speeds, and turbofan engines between the two. Turbofans are the most efficient engines in the range of speeds from about 500 to 1,000 miles, the speed at which most commercial aircraft operate. In a turbojet engine, the high temperature and high pressure exhaust gas is accelerated when it undergoes expansion through a propelling nozzle and produces all the thrust. The compressor absorbs the mechanical power produced by the turbine. In a bypass design, extra turbines drive a duct fan that accelerates air rearward from the front of the engine. In a high bypass design, the duct fan and nozzle produce most of the thrust. Turbofans are closely related to turboprops in principle because both transfer some of the gas turbine's gas power, using extra machinery, to a bypass stream, leaving less for the hot nozzle to convert to kinetic energy. Turbofans represent an intermediate stage between turbojets, which derive all their thrust from exhaust gases, and turboprops, which derive minimal thrust from exhaust gases, typically 10% or less. Extracting shaft power and transferring it to a bypass stream introduces extra losses, which are more than made up by the improved propulsive efficiency. The turboprop at its best flight speed gives significant fuel savings over a turbojet, even though an extra turbine, a gearbox, and a propeller are added to the turbojet's low-loss propelling nozzle. The turbofan has additional losses from its greater number of compressor stages, slash blades, fan and bypass duct, thrust. While a turbojet engine uses all the engine's output to produce thrust in the form of a hot, high-velocity exhaust gas jet, a turbofan's cool low-velocity bypass air yields between 30% and 70% of the total thrust produced by a turbofan system. The thrust generated by a turbofan depends on the effective exhaust velocity of the total exhaust, as with any jet engine. But because two exhaust jets are present, the thrust equation can be expanded. Early turbojet engines were not very fuel efficient because their overall pressure ratio and turbine inlet temperature were severely limited by the technology and materials available. The first turbofan engine, which was only run on a test bed, was a German Daimler-Benz DB670, with a first run date of May 27, 1943, after the testing of the double machinery, using an electric motor, which had been undertaken on April 1, 1943. Development of the engine was abandoned with its problems unsolved, as the war situation worsened for Germany. Later in 1943, the British ground tested the Metrovic turbofan, which used a Metrovic F.2 turbojet as a gas generator with the exhaust discharging into a closed-coupled aft fan module comprising a contra-rotating LP turbine system driving two coaxial contra-rotating fans. Improved materials and the introduction of twin compressors, such as in the Bristol Olympus and Pratt Whitney engines, increased the overall pressure ratio and thus the thermodynamic efficiency of engines. They also had poor propulsive efficiency because pure turbojets have a high specific thrust slash high velocity exhaust, which is better suited to supersonic flight. The original low bypass turbofan engines were designed to improve propulsive efficiency by reducing the exhaust velocity to a value closer to that of aircraft. The Rolls-Royce, the world's first production turbofan, had a bypass ratio of 0.3, similar to the modern General Electric fighter engine. Civilian turbofan engines of the 1960s, such as the Pratt Whitney JT8D and the Rolls-Royce Bay, had bypass ratios closer to 1 and were similar to their military equivalents. The first Soviet airliner powered by turbofan engines was the Tupolev Tu-124, introduced in 1962. It used the Soloviev D-20. 164 aircraft were produced between 1960 and 1965 for Aeroflot and other Eastern Bloc airlines, with some operating until the early 1990s. The first General Electric turbofan was the aft fan CJ8-0523, based on the CJ8-053 turbojet. It was followed by the aft fan General Electric CF700 engine with a 2.0 bypass ratio. This was derived from the General Electric J85 turbojet that powered the larger Rockwell Sabreliner 80 model aircraft, as well as the Dassault Falcon 20, with about a 50% increase in thrust to 4,200 lbf. The CF700 was the first small turbofan to be certified by the Federal Aviation Administration. There were at one time over 400 CF700 aircraft in operation around the world, with an experience base of over 10 million service hours. The CF700 turbofan engine was also used to train moonbound astronauts in Project Apollo as the power plant for the Lunar Landing Research Vehicle. The engine cores are shrinking as they operate at higher pressure ratios and become more efficient and smaller compared to fan as bypass ratios increase. Blade tip clearances are more difficult to maintain at the exit of the high-pressure compressor, where blades are 0.5 in high or less. Backbone bending further affects clearance control, as the core is proportionally longer and thinner, and the fan to low-pressure turbine drive shaft space is constrained within the core. Geared turbofans and further fan pressure ratio reductions may continue to improve propulsive efficiency. The second phase of the FAA's Continuous Lower Energy Emissions and Noise Program is targeting for the late 2020s reductions of 33% fuel burn, 60% emissions, and noise compared with the 2000 state-of-the-art. in summer 2017 at NASA Glenn Research Center, has finished testing a very low pressure ratio fan on a PW1000G, resembling an open rotor with fewer blades than the PW1000G's 20. The weight and size of the nacelle will be reduced by a short duct inlet, imposing higher aerodynamic turning loads on the blades and leaving less space for soundproofing. But a lower pressure ratio fan is slower. For GE Aviation, the energy density of jet fuel still maximizes the Breguet range equation and higher pressure ratio cores. Lower pressure ratio fans, low loss inlets, and lighter structures can further improve thermal, transfer, and propulsive efficiency. Under the U.S. Air Force's Adaptive Engine Transition Program, adaptive thermodynamic cycles will be used for the 6th-generation jet fighter, based on a modified Brayton cycle and constant volume combustion. Additive manufacturing in the advanced turboprop will reduce weight by 5% and fuel burn by 20%. Rotating and static ceramic matrix composite parts operates 500 degrees hotter than metal and are 1/3 its weight. GE is investing $200 million in the ceramic matrix. Composite will be used 10 times more by the mid-2020s. Rolls-Royce aimed for a 60-to-1 pressure ratio core for the 2020's UltraFan and began ground tests of its 100,000 horsepower gear for 100,000 lbf and 15-to-1 bypass ratios. Nearly stoichiometric turbine entry temperature approaches the theoretical limit, and its impact on emissions has to be balanced with environmental performance goals. Open rotors, lower pressure ratio fans, and potentially distributed propulsion offer more room for better propulsive efficiency. Exotic cycles, heat exchangers, and pressure gain/constant volume combustion may improve thermodynamic efficiency. Additive manufacturing could be an enabler for intercooler and recuperators. Closer airframe integration in hybrid or electric aircraft can be combined with gas turbines. Rolls-Royce engines have a 72 to 82% propulsive efficiency and 42 to 49% thermal efficiency, and aim for theoretical limits of 95% for open rotor propulsive efficiency and 60% for thermal efficiency with stoichiometric turbine entry temperature. As teething troubles may not show up until several thousand hours, the latest turbofan's technical problems disrupt airlines' operations and manufacturers' deliveries while production rates rise sharply. On a wide body, Safran estimates 5 to 10% of fuel could be saved by reducing power intake for hydraulic systems, while swapping to electrical power could save 30% weight, as initiated on the Boeing 787, while Rolls-Royce hopes for up to 5%. The turbofan engine market is dominated by General Electric, Rolls-Royce, and Pratt & Whitney. In order of market share, General Electric and Safran of France have a joint venture. Pratt & Whitney also have a joint venture with Japanese Aero Engine Corporation and MTU Aero Engines of Germany, specializing in engines for the Airbus A320 family. Pratt & Whitney and General Electric have a joint venture, Engine Alliance, selling a range of engines for aircraft, such as the Airbus A380. For airliners and cargo aircraft, the in-service fleet in 2016 is 60,000 engines and should grow to 103,000 in 2035 with 86,500 deliveries, according to Flight Global. A majority will be medium-thrust engines for narrow-body aircraft with 54,000 deliveries, for a fleet growing from 28,500 to 61,000. High-thrust engines for wide-body aircraft, worth 40 to 45% of the market by value, will grow from 12,700 engines to over 21,000 with 18,500 deliveries. The regional jet engines below 20,000 pounds fleet will grow from 7,500 to 9,000, and the fleet of turboprops for airliners will increase from 9,400 to 10,200. The manufacturer's market share should be led by CFM with 44%, followed by Pratt & Whitney with 29%, and then Rolls-Royce and General Electric with 10% each.